Well, welcome back, and we're going to look at this morning delving into rates of reaction, which is what we've been leaning into in terms of talking about collision theory and talking about how reactions progress. Now we're going to start talking about how we actually define this in terms of rates of reaction, how it makes our reactions faster or slower, and how we talk about those. So let's get started. So we all know that chemical reactions happen in different speeds. We can have really fast reactions and really slow reactions. Like the examples that we see in these pictures, a really fast reaction would produce an explosion, whereas something like rusting will occur very slowly and we can't see it happen in a particular period of time. So there's a number of factors that can change the rate of a chemical reaction. And when we talk about rate, we're really talking about the speed of a chemical reaction. And this can be what state they're in, what type of reaction they are, and things like that. So we talked about collision theory, and we said that for a reaction to occur, we need a fruitful collision, so one that has the correct orientation and the right amount of energy, that amount of energy being energy equal to or greater than the activation energy. So what we're talking about is the greater the number of collisions between the particles, the more chance we get statistically of there being a fruitful collision, and the more fruitful collisions we get in a set period of time, then the faster the reaction will be. And of course, if we're talking about rate, then we need to remember this time factor. So if we think about this, we need to sometimes speed up or slow down chemical reactions. Okay, so sometimes we may be wanting to slow a chemical reaction down, such as rotting food or things like that, because we want to store food for longer for transportation. Sometimes we want to speed a reaction up because we want it to occur faster. So if we're trying to make something through a chemical reaction in order to make more money, we may want to make more of it in a shorter period of time. So in this way, it's important for chemists to understand how we can control the rate of reaction. Okay, and there's an additional clip here for you to watch, which will talk about that, and we'll look at it in class, but let's move on. So when we talk about rates, the key factors that can affect the rate of a chemical reaction are temperature, concentration of the reactants, surface area of the reactants, agitation, so stirring or mixing, and the presence of catalysts. Remember, we talked about activation energy, and catalysts will act on our activation energy. First one we're going to look at is temperature. Okay, so if we think about temperature, if the temperature of a reaction affects the rate of the reaction, and we know this, okay, if we heat things up like cooking, if we were to put roast in the oven at 40 degrees C, it's going to take forever to cook. In fact, it would probably never cook. Okay, because it's not going to reach the activation energy to cause the reactions involved in the proteins when we cook something. But if someone came in and turned the oven up to 280 degrees, we also know that that wouldn't work particularly well because it will cook more quickly, but it's going to cook rapidly from the outside where that high temperature is, and we would end up with something that was all burnt and charred. Okay, so as chemists and as scientists, we need to be able to manipulate the rate that a reaction occurs to get the desired outcome. So if we look at this, when we talk about the effect of temperature on rate, then we need to look at a number of factors. The change in rate due to temperature can be related back to the particle model and collision theory. So we're going to set it back to the idea that particles are always moving and collide into each other. When we increase the temperature, what we do is increase the kinetic energy. So we increase how much the particles are moving. Okay. So if we increase the temperature, then the particles are moving around much faster. This means the molecules move faster. Because they're moving faster, they collide more often. Much like if we have a busy road and it was peak hour and we made everybody drive at 80 kilometers an hour instead of slowing them down, there would be more collisions. Okay, because there are more collisions, then they're going to increase the rate of reaction because now we have a higher chance of there being a successful collision. Okay, the greater number of collisions in a same period of time, and they have more energy, so they're going to meet that energy requirement. So there's a two-factor aspect with temperature where we increase the amount of collisions in a set period of time, but we also increase the energy of those collisions. So we see a greater effect on the rate of reaction. We describe this as the greater the number of collisions, the greater the proportion of successful collisions and the faster the reaction rate. Okay, because not every collision will successfully result in a reaction, but if we have more of them, then there's a greater chance that we will get more successful collisions. So when we look at this diagrammatically, we can see that if we slow a chemical reaction down by lowering the temperature, then the molecules are moving much slower. Because they cover the distance in a more slow manner, there's fewer collisions, and when they collide, there's less energy. If we increase the temperature by increasing the energy of the system, then they're now moving much, much faster. These lines show speed lines, okay? They're moving much faster. They will collide more often. They'll just bounce around and hit each other more. And when they do, they will have more energy. So first things that we're going to do when we get back into class is look at a demonstration. And that will be looking at the effect of temperature. So that's the last one I want to talk to you about today, and I'll see you in class.